Good afternoon, everyone. Welcome to the North Dakota State Championship celebration. No, wait a minute. No, this is the Agile MBSE Lunch and Learn series with Dr. Bruce Powell Douglas today, and he's this is now session 7 of 8, and today we're going to be looking at the model-based testing, what it is and how to do it. So I am our chapter is hosting it today. I'm from the Wright Brothers chapter. We're located in the Southeast Ohio region, and I'm Dr. David Long, and I'll be your cruise director for today, and we'll turn it over to Dr. Douglas here in a little bit. Just a little bit about where we've been on our journey here. Starting in September, we started with the Agile modeling, and now we're up through the testing, and then later this month on the 26th, we're going to be talking about MBSE and safety analysis. MBSE does lots of cool stuff, and a lot of people probably never thought of doing the safety aspects with it. If you want to get a hold of the previous 6 recordings, they're available to you, and they usually pop up 1 to 2 days after the session. But just Google and look for Dr. Douglas's YouTube channel, and there's a wealth of information there. It's really cool. You can also go to the Great Lakes National Council Regional website, and we have links there too. Some other things that are coming up: the regional conference, which has been postponed because of COVID again, and we're looking for an alternate date, targeting right now the fall. And we've got a challenge teams program that's coming up, and we're starting to do planning on that. So for those of you who are new to NCOSE or are here just checking us out, a little bit more about us. We are all about systems engineering. It's the International Council on Systems Engineering, and we help advance the field, and we provide support for people, and we provide resources for them too. We've been around about 30 years now, and we've got 19,000 members, 74 chapters, 35 countries, lots of working groups to look at all the different areas that are important to systems engineering. And we have a certification program where we have over 3,500 systems engineers certified. Those chapters, like I said, are all over the world. We have them broken into 3 chapters or sectors. The first sector is the Americas, and you can see that we've got 46 of those chapters, and we're broken into regions. Go to sector 2, and that's the green area on the chart, 16 chapters across those areas. And then sector 3, if you're in China or India or Australia, you can be in sector 3. So we have the Great Lakes North Central region, and we have expanded beyond just this cluster that's around the Great Lakes. We've moved into Canada, and we've started to move down south and west too, and we're down to the Great Plains. We're in the Midwest, Heartland. So we are in the central United States, and we've been moving expanding beyond those areas. We've got a program called the Corporate Advisory Board. So if you're a member or if you're a employee of one of these companies, you can be a CAB member, and you can show up at the meetings, and you can register as an associate member, but you're not a voter, and you can't have a position like a presidency or one of those positions in the organization. I talked about the 55 working groups, and we have lots of them that are growing. We've got people that are working on each one of those in the leads, and if there's an area there that you're interested in, jump on in and you can find them. And it's growing, it's changing. We'll be combining and separating them where it seems to make more sense to do that. We do have an international workshop coming up at the end of this month, and registration is open. And this is going to be, it's been changing back and forth. I think it's blended right now. So if somebody, yeah, there we are, it's a hybrid event. And you can either go in person, or you can down to Southern California, or you can participate from your desktop computer. Either way. Right. So with the, if you want to learn more about becoming a member, just go to incosi.org, and there's lots more to learn about. If you're interested in becoming a certified professional, if you want to join a chapter, if you want to be a volunteer or take on a leadership role, all things that you can find in there. So every time, or excuse me, with every one of these sessions, we are giving out one of the copies of Dr. Douglas's book, the Agile Model-Based Systems Engineering Cookbook. And I've had people come back and say, wow, this book is absolutely amazing. It's exactly what I needed. And so it's a great resource for several people. So last time, Doug Junker out of Edina, Minnesota, North Star chapter, and he works at Medtronics as a systems engineer. So he's up there in the North Country right now, freezing a little bit, and maybe he's got it. I don't know if he's with us today or not. I didn't look on the list, or if he got his book and said, I know everything now and doesn't have to show up again. So the book will be autographed, and it'll be a random drawing. Somebody is going to whisper into my ear at some point and tell us what the book is going, or who is going to be the winner. And then I'll be announcing that at the end of the session, but you must be present to win. That might be how I get mine. If everybody else leaves, I'm still here, I get the book. So without any further ado, we're going to turn this over to Dr. Bruce Powell Douglas. And he has written this book, and he has based it on a long experience of working in systems engineering and model-based systems engineering. So he's co-authored other books. He's got over 7,000 pages in his books that he's done, a lot of different places that he has contributed. So with that, I'm going to turn it over to him, and he can have the rest of the day. How's that? Dr. Douglas, are you with us?
Yeah, I am. That sounds good. Let me share my screen.
And I will stop sharing mine.
Yeah, it says you can't share until this. Okay, let's try this again. There we go. Okay. So welcome everybody to this session 7 of this Agile MBSE series. Today we'll be talking about model-based testing. So with that, let's go ahead and get started. Oh, I should mention I'm a principal of a priori systems, but I'm also the senior principal agile system engineer at the Meyer Corporation. So I do a couple things. Here we go. Okay, so first of all, what the heck is model-based testing? So many people think that it's testing models. That's not actually true. You can use it to test models, but you can use it to test software or systems or other things as well. Model-based testing is the application of modeling to testing. Modeling brings a lot of value in terms of understandability and formal semantics and simulation and executability to the development work, as both specification of requirements and capabilities, and to design and architecture and so on. Well, models can bring the same source of value to the process of testing. And that's what we'll be talking about here. So what I mean by model-based testing is using models to specify, implement, and apply testing to systems. Well, systems may be models, or they can be other things as well. There is a standard called UML Testing Profile, first released in 2013. Current version is 2.1. Although I checked with both Cameo, Magic Draw, and Rhapsody, and the current implemented version of the profiles in those tools is 1.2. But fine. It is a standard way of using UML or SysML to specify test work products, test components, capture test information, and present such information. And here's a link off if you want to go read the specification. Here's a link off to that as well. So before we talk about what's inside the testing profile, I want to talk about specification and design models. In principle, there are three kinds of models here for such systems. There's the specification model, which deals with requirements and capabilities and so on. There's the design model, which implements that specification. And then there's the testing model, which tests the design model against the specification in the specification model. So logically, these are three distinct models. They can all be in the same project, whether it's a Rhapsody project or Cameo project. They can be in the same, project. So Cameo project doesn't quite equal model. It can, but they're not completely overlapping concepts. But a Cameo project or Rhapsody project can include kind of packages which are themselves models. So it's not uncommon to have, in your model, one big package, which is my specification stuff, all my requirements, my use cases, my capabilities, my user stories, and so on, just like we talked about in previous incarnations of this talk, previous episodes. Then there can be an architecture design model where we specify what the system content is and how it behaves to comply with that specification model. And in another high-level package, we've got all the testing work products, testing artifacts, for testing the design model against the specification model. In the design model, the thing you're focused on testing is called SUT, or system under test. For the purpose of testing, it can be an individual block or class, operation or context or collaboration or interaction. That can be an entire set. So it can be any of those things. That's called system under test. And it's the focus of the testing effort for some testing effort. And you can test every different block in a design model at the different SUT. You can have the SUT be the collection and collaboration of those design elements. That's really kind of up to you. Those are the kind of key concepts around, high-level concepts around the models. This is an abstraction of the meta model within the UML testing profile. We see some elements here like the SUT, the system under test. This would be either the entire or some portion of the design model that you want to verify. And by the way, I should mention that you can also test your specifications. So I built a lot of what I call executable requirements models. I've talked about this before in previous episodes. And I want to make sure that my specification model is in fact complete, consistent, and accurate and correct. So I will actually test my specification models before I hand them off to the design team to go off and build it. So I can actually also use my specification model as a design model to verify that, yeah, that's actually what I meant to say before we go off and implement. But anyway, some set of elements within that are what we call the system under test. Then there's these test cases. So test cases are a particular test where you have a particular set of inputs, done with certain values and timings in a certain context with an expectation of an outcome or output. These can be represented in four kind of key ways in the testing profile. They can be sequence diagrams, which is the most common. They can be activity diagrams. They can be state machines. And sometimes you just write code snippets in a scripting language. That's okay too. But these are your testing scenarios. So your testing context will have a set of these test cases which you will apply to the system under test to achieve test objectives. The test architecture are the elements of your test model used to implement and perform the testing. The most important of these is probably the test component. These are the testing stubs that you'll create to drive the testing or support the execution of testing, and as well as an arbiter and a scheduler. These can either be manually created or they can be automatically generated if you have automation to do so. I will show you both cases in this presentation. And then finally, you have test outcomes. So this is represented as a test log. We have a set of text executions of your test cases. Each one of these will have a verdict, which will be it passed, it failed, it was inconclusive, or there's some error running in this case. Pass or fail is by far the most common sorts of things. And this is kind of a high-level overview of the testing profile meta model. So as I mentioned, when we capture test cases, the most common thing to do would be to do sequence diagrams. So if I've got 10 test cases, I've got 10 different sequence diagrams that I apply to my system under test to see whether or not it's right. I can also specify these with activity diagrams, state machines, or even code snippets if I want to do that. So while you can do this informally, and I'll show you what it looks like in just a minute, you can also do it a bit more formally and apply the testing profile. Both Cameo and Rhapsody include, or optionally include, the testing profile. Cameo comes with the tool, with Rhapsody as an add-on, cost plus, with all kinds of automation called Test Conductor. And we'll actually see an example of Test Conductor later. Specifying particularly complex test cases, not as so much as scripts, but as ways to represent complex behaviors with sequence diagrams and activity diagrams brings clarity. A lot of times it's easier to see how the test case unfolds over time for complex test cases. It's easy to trace to the requirements, which may be in your specification model. So you can specify that this test case tests the following sets of requirements as it steps through the different invocations of behaviors as a part of the test case. You can also import test cases from like CUnit or CPP unit, JUnit. That's possible. I've seen that done as well. And then render them in the tooling as test cases. As I mentioned, you can be done manually or automatically. So let's look at an example. And first, we're going to walk through this manually. In this case, we've got our system under test, which is this block named Tokenizer. The upper part is what you might see on a BDD in SysML. And there's this client here, which is going to be our testing component. So informally, I call these testing buddies, and they're just test components of things you make to facilitate or perform the injection of events of interest or invocation of behaviors or setting of values, setting up the test infrastructure for performance of the test case. In the second part down below, we see what it might look like on an IBD, where we've got these parts communicating, and this is, of course, a connector rather than an association, but it's typed by this association out here. This particular case, the tokenizer, what it's going to do is it's going to receive digits from a string. They'll have characters like quote 1 and quote 2, 3, dot, 2, 3, 4, 5, something like that. So you've got this string of representing some value. And it's going to take those in one character at a time from the left side, and it'll construct a real value based on parsing the incoming events. And the incoming events will either be, here's a digit, in which case you'll pass, along with that signal, you'll pass a character 1 or a character 0 or a character 9 or something like that. It'll be a dot event, in which case it's a decimal point, or it'll be a white space event indicating that you're done with that string. So if you get to the end of the string or you have a space after the number, that's white space, and that says, okay, you're now done tokenizing that value. This is what that state machine is for that tokenizer. This is the classifier behavior for the tokenizer block. And we see, pretty simple that it starts off with, we don't have a number, and then we get a digit. And this here is a peculiar way that Rhapsody indicates for passing a value. It builds a struct called params, you dereference it. It's a Rhapsody specific thing. Cameo has its own little steps you have to jump through to get the value from the signal. So we get the value from the signal, we assign it to a local value called CH, which is our character. And then we go into got a number state and the nested state processing hole. Along the way in, we set the result equal to 0, and we set another value property called tens place for the fractional part equal to 10. And we process that digit. Result equals result times 10 plus the digit value of that character. So if it's a quote 9 end quote, it gives you the value 9, which you add in to the result. If you get further digits, we do that again, in which case we move it over one decimal place by multiplying it by 10, and we add the digit. Once we get a dot, then we start adding fractional parts, and that's in the processing fractional part state. We take the result and we add in the digits value, and we divide that by the tens place. And then we augment the tens place by a factor of 10. So if it's 0.2345, first you have 0.2, and then tens place is 100. Then you have add in 0.03, because now it's 100. And next place will be 1,000th place, and so on. So we build up a number. And when you get white space, then we print out the result and we're done. Pretty simple state machine. So we can create our test cases as sequence diagrams. So here we've got, I'm sending the EV digit where I'm passing the value 1 or 2, a dot, 3, 4, white space, and then we see I expect the result to be printed. So this is what I expect. And here I've got a condition mark saying, well, what I expect is the value of result here is 12.34. In this case, I'm going to send 00.78, in which case I expect the result to be 0.78. And in this case, we're sending .78, in which case I expect the same result, 0.78. So I take my test buddy, this client class, I can implement that as a state machine. So I said that the most common thing to do for implementation of test cases with the testing profile is sequence diagrams. Personally, I do it with state machines a lot. So here we just using a macro defined in Rhapsody, we're just sending out to this reference property. So here's the reference property, it's Tokenizer. Sending out to that reference property this signal with this value. So the digit carries a 1, a 2, a dot, 3, or 4, and that's test case 1. So then as a tester, if I go to the client and I send, as a tester, send the client, okay, do test 1, it will do this behavior, it'll invoke the Tokenizer. If I send test 2, it'll do 00.78 and so on. I can do something very, very similar in Cameo with the action language helper .send signal helper function. And I didn't do that in this case. We'll show you what I did for Cameo, just to show you an alternative approach. But this is my testing component used to drive the Tokenizer for the test cases that I've defined. Same thing in Cameo, looks like this. So here we've got our BDD. So BDD, and Cameo requires a context for owning the BDD. Rhapsody does not. So here I've got a system which is providing context, and I've defined the BDD where I've got a connector implementing this association. Here's the state machine, which I'm using a different scripting language. The previous one was in C++. This is in Groovy. Fine. So the actual language is slightly different, but you can see it's basically doing the same thing. This, however, is how I implemented the client. Let's look at that in more detail. So this is how you do things in Cameo. And again, I could have used the action language helper to do it like I did something similar in Rhapsody. But here we're sending the send character event, where I'm sending a 1. So here is the activity I'm invoking, where I pass in the character as the value being passed in. And in Cameo, I've specified the target pin on the digit event. To do that, I need the reference property and I need these the read self. So it it can be done. It's just a little bit more work in Cameo than Rhapsody, but the same thing can be done. And so this is how I'm sending the digit out. And so you see I send a 1 and I send a 2. And then here I send 3 and 4. To send the dot, I've got another one here which sends the dot. Basically, I just specify the target where it goes. And here I'm sending white space at the end. And here I'm sending the white space event signal here. So pretty much the same sort of thing, except I use an activity diagram to drive the client behavior rather than a state machine as I did in Rhapsody. So this is what the execution would look like. This is the animated sequence diagram. It's called a witness scenario that we created from the execution. So I'm going to insert the event. I'm going to run test case 1. And we see it runs. And we see it's executed here. And we can look at the outputs. If I look, I didn't show the standard output where the print statement goes, but if I looked at that, it would be there. And here I can see I can run the next test case. So pretty straightforward. Let's do the same thing in Cameo. Well, almost the same thing. In Cameo, what I'm going to do is I'm going to use this test case scenario to drive the execution of the system or of the SUT. So in this case, I have for the system block, I've defined a behavior called test case 1. The sequence diagram, and it's owned by the system block. And I'm going to run this to drive the interaction. So let's see what that looks like. I capture this in the video. So I click and I run simulation down here, simulate with context. And it starts running. And I say go. And we see that as it walks through this, it drives the state machine behaviors. We see the active behavior being shown as we execute. And at the end, then we'll see the result printed down here, 12.34. So again, what I expect. Now I can also create what's called a witness scenario. So remember, I mentioned really quickly before, the witness scenario is a scenario drawn from the execution. So it's nothing you hand draw. The test case you typically hand draw. Although you can, with sufficient automation, create those automatically as well. But normally you hand draw the sequence diagram. This is what I want for this test case or that test case. The witness scenario, on the other hand, is what actually happened. Then you can compare the two. Did what I expect to happen actually happen? So let's go ahead and create a witness scenario. To do that in Cameo, I go down here and I say, okay, create me a sequence diagram from that execution. And it creates a sequence diagram. And then I click on go, and it executes that, drawing the sequence diagram from the execution. And again, we see the same output, 12.34, in the console output window. So what does that witness scenario look like in Cameo? This is what it looks like. So you'll notice something I find kind of interesting, that there's 2 lifelines here corresponding to Tokenizer. Now remember, I didn't hand draw this. What I said was, create me a sequence diagram from the execution. That's what I said. What Cameo actually did is it drew the same instance as 2 different lifelines. One showing the state invariance as we go from state to state, and the other one showing the message exchange between the elements as they exchange messages. But these 2 lifelines, this one here and this one here, are the same instance. They're not different instances. There's only one instance running here of Tokenizer. So in this case, where you got 3 lifelines, that's not really a problem. If you had, say, 15 lifelines and half of them were replicated, went from 15 to 22 lifelines, that would be a problem. Just saying, that's a little weird. But at any rate, you can see this witness scenario being created, and this is stored in the model. You can also see down here the console, the resulting output from these print statement down here. These little annotations marked as constraints here are the result of the setting of values. So here we changed the pass the value in. And one of the things we did remember, we set ch equal to the passed value. So we set it to the quote 1 end quote, it's a string. And result was assigned the value 0. Tens place was assigned the value 10. Then we get the 2, and result was moved over, multiplied times 10. And then we added the 2 value in, and so on. You can see how the changing of values takes place during the execution of the test case. And this allows you to look at not just the final outcome, but also where along the way it might have failed. Well, in step 6, I saw this, but I expected to see this. And that's where the test case failed. And that really help you in debugging your system under test later. So as you run this manually, you have these test outcomes. You can then compare these to the witness scenarios. So these are the witness scenarios. You can compare them to the test case specifications that you had before to see, did what happened meet my expectations? And if it does, you say passed. And if it doesn't, you say, well, failed. And you have to figure out why it failed and what the problem was. The problem could either be in your design, the design was wrong, or in some cases, the specification was incorrect. So here we see what they look like side by side. I know Rhapsody has a tool for sequence diagram comparison. So you can select the sequence diagram and in the tools menu say, okay, compare it to another one, and it'll highlight the differences between them. So you don't have to just manually inspect it. Cameo may have this feature, but I've not used it in Cameo, so I can't speak to that. So that's manual. So both Cameo and Rhapsody both support and have the testing profile. With Cameo, you get it as a free profile that ships with the tool. With Rhapsody, it's a cost plus add-on. But for the cost plus, you get a lot of built-in automation. Whereas Cameo, you've got the profile defined, but you have to do everything manually. You have to do everything, apply it kind of manually in individual manual steps, which can be done, but I do like the automation. So to do that, to apply it, I load in the testing profile in Rhapsody. I select the elements that I want to use as my system under test, and I say, create test architecture. And it generates, in a separate package, it generates this test component called test context tokenizer. It creates a part, stereotyped system under test, and creates this test stub for every element that there are relationships which connect to the system under test. In this case, there's only one, which is the client. So, but it creates a driver for that. And it'll use that driver to then run and execute the test cases. All of this is created automatically when you say create test architecture. Then you specify your test case. So you'll select the sequence diagram, you see create a test case, and it'll create a test case where we see here's our tokenizer lifeline, our system under test. Here's our driver. And we say, I've got in this case, specify .78, send a white space. In addition to just executing the steps, I also want to make the assertion that the result is the right value. If you actually run this, the value you get, this is both true in the Cameo model I put together and in the Rhapsody model, the actual value will be 0.7799999999. So really, it's just round off error because that's how real numbers play, right? You get round off errors. So the actual assertion you want is not that result equals exactly 0.78, but accounting for round off error, it's right. So in this case, I say 1 part in 1,000 is close enough. All good. You could make it 1 part in 1,000,000 or 1,000,000,000,000. That's up to you. But here's my assertion. Not only follow these steps in this order, passing these values, but also the resulting condition is true. That's an additional test condition you can add. So as I run this, and I can have Test Conductor run not only one test individually, I can create a suite of test cases and say, run the suite, and it'll actually create a little view of all that. We've got, here we've got test case 0 and test case 1 and 2 and 3. It'll actually run all of these and show you whether they passed or failed. And then it'll create, and again, put this in the model, an HTML file, which summarizes your test outcomes. So here's the test case result, who ran it, when it was run, what version was run, various test case summary statistics, and how each one ran individually. That's called the test report. And this is visible in Rhapsody tool, or you can double click on it and open up your browser to look at it. So let's look at a slightly more elaborate example. This comes from the Test Conductor training materials, and I use this with Otto Brockmeyer's permission. So thank you, Otto, for that. So here we've got a coffee machine, and we've got a number of blocks inside, number of parts inside, represented by blocks, coffee beans, water, grinder, brewer unit, and the controller with relationships here, including a port connection to the outer boundary of the coffee machine. And we're going to use as our system under test this controller, which controls the making of coffee. So when I create the test architecture, it creates this test components, tcon underscore context, the controller rather. That's the name of the overall block architecture, and then a test stub for all the things it connects to, and then marks this in part as a system under test in this context. And then we can add test cases. And in Test Conductor, I can do any of the standard ways. Most common would be adding sequence diagrams, but you can do it as an activity diagram. A flowchart in Rhapsody is just a dumbed down sequence or activity diagram. Flowchart is just an activity diagram without the concurrency semantics. So it's just a single flow. So you can do that. You can, as a state machine, or you can write a code snippet to do that. And they have a bunch of macros here for doing special things that have special meaning to the Test Conductor tooling. Assert, when you want to assert. At this point, I want you to check that this is true. And as part of running the test cases, the assertion returns true. Now, when you run the test case and you create the witness scenario, Test Conductor will look at the resulting witness, compare it to the expectation, and mark things that are beyond what is expected. So here we see these are in green, that's what I expect. This one marked in red, now that's a deviation from what I expect, and it tells you what the deviation was. In this case, we're called get water, and the value passed was 6, or expected to be passed was 6. What was actually passed in the execution was 5. So that's a violation of my expectations. That means the test failed, and it failed at step 4. So the report you'll get will say, I failed at step 4, and you can go look at this and say, well, let's go find out why, in this case, it was passing the value of 5 when I expected to see 6. And then once you get it all work, then you can look at the case results. So the one I've shown here is when they all passed. Now that's a lot. And automation is really useful when you're testing complex systems. You don't have to create all the testing infrastructure for yourself. And that's good. But there's more. It also gives you model coverage. So if you have a specification model, you might want to know, well, how much of my specification was actually covered. So the specification model, we specify things in state machines or activities or some behavioral means. How much of that was actually visited as I executed my test cases? This provides a summary of that coverage. So here in this particular case, we covered EV on, event reception, the various states of the state machine and the various elements of the state machine, but marked in red are the parts that were not covered. So this gives you model coverage for your model-based specification. If you're generating code, you can even get from the test conductor code coverage. This is required for a number of standards, such as GO 178, which is an avionics, civil avionics safety standard, which requires different levels of coverage for different criticality capabilities of airborne systems. And you get coverage for statement coverage, decision coverage, and MCDC coverage, which, depending upon whether you got level D, C, B, or A, criticality is really important for certification of your systems. So when you're generating the code from the models, which is a pretty common thing in Rhapsody, you can use this to also get statement coverage. So you see that there are some statements here that are not yet covered by your test cases. Oops, sorry. Skipped ahead. And that's really valuable too for automation, because this is one of the places, particularly when you have level A certification needs and you have to get MCDC coverage. That's a pain. That's just a lot of extra work, and Test Conductor can really help with that. Wait, there's more. There's one more feature, which is an add-on to Test Conductor called ATG, or Automatic Test Generator. And it can walk over your specification model and create a set of test cases rendered as sequence diagrams. That's the only way I've done it anyway, to create full coverage of your specification model. And so this is what it looks like when you're doing the test case generation. If for some reason it can't generate a test case, for example, you have a guard conditions on your state machine, which may not be obvious, but there's no case where you can actually get to the target state because of the guard conditions. And then, that case, you'll get an error message. You can say, I wasn't able to generate test cases for these cases because it's just not possible to get there from here. That sometimes happens, and it means there's a problem in your specification model, but it does sometimes happen. So this will actually go through and walk over your model, your specification model, and generate your test cases from it. And here, because these all trace to requirements, the elements in the specification trace to requirements, like this state represents these three requirements, and this transition represents those requirements, and so on. You actually get coverage of which test case generated exercises and verifies which requirements, which again is really valuable, particularly when you go for safety certification. All right, so let's talk in summary about the model-based testing. First of all, testing's hard. I mean, testing really is tough. A study I read a few years ago found that for embedded systems where they're an embedded computer doing a dedicated job with the software doing the work, that testing was over 60% of the cost. So it wasn't in specifying or doing the design work. 60% of the cost was actually verifying and getting the system to actually work properly. So testing is a big deal. And if you can save money on testing, you're ahead of the game. That's a real value. Now remember, the models are always simplifications of the real situation. And simplifications in two ways. First of all, models only represent things of interest, aspects of interest of a system or a context, and they just ignore things that you don't care about. So they're an abstraction in that sense. They're also abstractions in that the amount of detail represented is necessary to support the purpose and intent of the model. Real systems have essentially infinite level precision. Real systems or your actual models do not. They stop at some level of detail and say that's enough to meet my needs. So models are always simplifications of the actual systems that you're going to test. Models provide significant enhancements in our ability to deal with engineering data because life is complex. And that data includes requirements in design and implementation stuff. They can also and then enhance our ability to do testing. You can create test architectures from model structures. You can develop and represent test cases and evaluate them in a more straightforward sense. I think on code-based testing, that's my experience. Your mileage may vary. Execution of the test cases against the system under test and the test architecture. So you actually run the test cases in your modeling environment. You can compute the verdicts automatically, depending upon automation and stuff you have in place. And then you can determine coverage, both model coverage and potentially, if you're doing software intensive systems, code coverage as well. Testing Profile provides a standard way of doing testing with models, creating test components, doing your test cases, creating the test architectures, creating the test outcomes as your test logs. This can be done manually. I do this a lot for smaller systems. I'll just manually create my little test buddies, and I do that to exercise the systems under test. And I do this in an agile way. So as I create the system under test in an agile way, it's an incremental way, I'll do some portion of the behavior. I create some test components that necessarily exercise those aspects. In the next nanocycle, as I add more behavior to my element under test, I add more richness to my test components. And so they evolve kind of concurrently at the same time in an agile means. And so that's what I do when I do it manually. For larger scale systems, I really like the automation provided by the test conductor tool. That's a really nice feature. Creating my test architectures, assisting with the creation of the test cases, the execution, and giving me model coverage. I really enjoy that for larger scale systems. For small, toy models, not so important, but for big models, it saves a lot of time. And the automation of model-based testing provides some actual real benefits. Repeatable testing. So I can apply the test cases again because I have them all in models. I can auto-generate test architectures, test suites, and outcomes. I can even create test cases from ATG if I want to do that. So with that, that's what I had to talk about on this brief whirlwind tour of model-based testing. There aren't a lot of books out there on model-based testing. I do talk about model-based testing in my books, but there is this book from Springer that's actually a pretty good book called Model-Based Testing. And there are also, like I said, there's the standard profile available from the OMG, and there's some additional information on my website. So with that, I will pass control back, and I'll let David take control.
All right, thank you very much. Before we get into the Q&A session, we've got some really important business, and that is finding out who won the autographed book, the Agile Model-Based Systems Engineering Cookbook. And so the name was drawn and sent to me, and I told Jack that he misspelled my name. And the way that he spelled it, it looks a whole lot more like our winner is Norm Eckhart of East Aurora, New York, and he's a member of our Finger Lakes chapter. So I see he's unmuted. So welcome, Norm.
Hey.
The microphone is yours.
Yeah, I'm glad to be here. Thank you very much.
So we'll have to make sure we have the right address so we can get that to you.
Okay.
Okay, with that part, oh, I forgot to ask for a drum roll. Oh, well, you just have to do it yourself at your own time. The questions that we got up here today. Let's see, so the first one came from Alvin Zetzo. Can this framework fit into the CI/CD pipeline or a CI/CD pipeline? I need to have more information than that, but maybe you know where he's going with it, Bruce.
I'm not sure what he means by CI/CD. Could you elaborate?
Yeah, so a lot of what I see that you're doing, it looks like you'd be doing it offline, but for agile software development, we're trying to actually move to a continuous integration framework where tests are, you do your test scripting such that when a developer does their push, then all of these tests are kind of run automatically, called by Jenkins or whatever your test that side of it. So I'm not sure how, doing the test case and test scripting in Rhapsody could be called by Jenkins. We'll be curious if others have, thoughts, opinions on that, or maybe you can elaborate, like, how does this fit into continuous integration for agile software development?
Okay, so CI was continuous integration. That was the part I was missing. Yeah, so I do know people that do script automatic execution of test conductor to perform test cases in their agile environments. So yeah, there's no reason why you can't do this by just saying, here's my test cases. It's just a development environment, an execution environment for the test cases. So the fact that you kick it off from a command line is a perfectly reasonable thing to do. So yeah, people do that. I do know people that do that.
Okay, thank you.
Okay, so then the next one, Andrew Buxton, is the test condition part of the UML testing profile or some usage of SysML? And he referenced your slide 21 on that.
I need to go back and look at the meta model, see if there's what the condition are, how the actual meta model is rendered. But it's a pretty common thing to have. So I think it's part of the test, because you can specify a test case with basically a scripting language, and that's all the assertion is a statement in an action language. So I don't see any issue with that as not being part of the standard, because it's just a statement in an action language.
Okay, Andrew, I don't, is he still here? Is that?
Yep, I'm here. Thank you, Dr. Douglas. That makes
Okay.
sense. Thank you.
All right. Another question is, can Gherkin be used to specify test scenarios? And if so, does it execute?
Not used Gherkin myself, so not sure. That's a tool specific question. Do you have that as available action language in your tool? In Rhapsody, you don't, at least not directly, because Rhapsody supports 4 languages out of the box: C, C++, Java, and Ada. But it doesn't mean you can't, with Java API, invoke another execution environment, because I've seen people do that, but it's not directly supported in the tooling that I'm familiar with. Doesn't mean you couldn't do it.
So Andrew came back and asked another one, saying the presentation that you did here, you're looking at the model representation of the system, and just, let's see, you showed how the model representation of the system is tested. Have you been successful with examples of testing the actual hardware or software from test cases defined in the model? And then how has this been automated?
Yeah, I've seen system people do this where they, again, mostly my experience with this is in Rhapsody. But because Rhapsody generates actual deployable code from your test model, you generate deployable code, and it can control actual hardware. And so you can use this to actually control the actual hardware in the lab to drive physical things. So yeah, I have seen that done.
Okay, thank you, Dr. Douglas.
As I was going through this and listening, I had a question about the applicability. Are there categories or categorizations of your systems under test, whether it's a hardware, a software, or some type of system? Are there some types of these, the hardware or software, that works better than other methods or than other types of systems? What are the best systems to use for this?
Well, I'd say certainly software intensive systems are certainly the most straightforward to apply. But anytime something has behavior that is a change of value over time, change of a condition or value over time, that can be ascertained either with a sensor or by a computational evaluation, it can be used. Things that you can apply, suppose that you say you have a requirement that this should last for 6,000 hours of use. That's not a behavior per se. How would you test that? Well, you could run it for 6,000 hours, see if it still works, but that'd be onerous. Or you say, we're going to paint the requirement, the plane is painted green. That kind of a non-functional requirement. That's more difficult. But when you have behavior, you can ascertain behavior as well as properties of behavior, such as timing. This has to happen in no less than 100 milliseconds. You can do that as a test case. But this has to happen and the light is aqua. That's harder to test, right? So things that are not verifiable either by looking at a behavior or evaluating computation are difficult to ascertain. If you've got a mechanical chain drivetrain, and you want to look at, this should now be in, chain ring 3 of my bicycle. If I haven't instrumented that with a sensor, how do I ascertain correctness other than visual inspection? So, so while you can do it that way, it's less obvious, I'd say. Certainly the low-hanging fruit would be software-intensive systems, or systems that you can monitor with sensors that return software information.
Okay. We got one from let's see, who is this? E421485. How do the changes in the design model, or let's say, how do the changes in the design model can be applied to the testing model? So I guess how do we apply the changes? If our design model changes, how can we test?
Okay, well, what do you do now? What you do now is you go off and you change your test cases. That's what you do now, right? Same is true that if your design model changes, you may eliminate that, you may break the test cases because the design no longer works. On the other hand, if your specification model changes and you're automatically generating the test cases from the specification model, you can regenerate those test cases. But otherwise, if you're doing it in a manual way, you'll have to manually recreate or update your test cases. So if the design model changes, and so, for example, your part of your specification is, this value property has this value, but in your change design, you remove that value property, you'll have to change the design, or just mean the test case, to reflect that change in the design.
I'm not sure who E42 is. If that was a phone calling in, or who that was. Right. So let's see, how can this UML or SysML modeling be applied to test cases involving artificial intelligence machine learning components where continuous learning within the operating environment is key?
Well, the same with testing now, right? So there's two parts to do machine learning testing. One is you want to test the machinery that supports the machine learning. So I think of this is a big topic, but I think of machine learning systems as kind of like hyper software, because the software is the neurons and their connections and the layers of the neurons. and the manually and how you do the centroids of the weights and so on. That's the infrastructure. And you need to test that infrastructure as well. Then you have a machine learning system, which is this hyper software, where all the software, in quotes, is really a function of the relative weights of the different connections in your linked system, right? So that's how neural networks kind of connect. So the software isn't in lines of code. The software is in the weights of the different connections. So to test that, how do you test it now? You probably have a number of exemplar cases where you used for initially ones used for training. Did you do, and during the learning process, you create an optimization which tries to simultaneously come a solution that best fits all the cases of the exemplars. That's how machine learning is kind of trained. Well, you'll run your exemplars to say how well does it meet all those, and is it within my tolerance? Does it the right answer, plus or minus some range that I expect? You also additionally test for novel cases. So think of a machine learning where you're learning to recognize using optical sensor, hand-drawn characters. And you test with, 10 people who write out alphabet in words, and you can recognize them sort of best case. So then you look at Susan, who wasn't part of your exemplar case, and look at her writing and say, can you recognize that properly? So that view in the test cases, that all of those can be represented as test cases in such a system. I hope that answers your question.
Okay, then we
Yeah,
have
thank you so much. Yeah, that answered my question. Thank you.
okay, the next one is from Michael Enoch. He's got a question about system timing performance and the how do you use system timing performance with Marte or another approach to define the timing performance?
Okay, with Marty, Marty is an extension or an elaboration. It's version 2 of the SPT profile. I'm one of the authors of the SPT profile back in the day, and Marty, I wasn't one of the authors of the Marty profile, but it's meant to, for those people who may not know, it's the model analysis real-time embedded systems. That's what the acronym stands for. In that, you have a bunch of stereotypes that define kind of standard constraints, standard tags that you can apply to model elements to reason about timing that you want to specify. So the system is right if worst case performance of this action is less than 100 milliseconds. So it's a way of specifying these constraints. Well, those become the assertions in your test cases. So you would assert that the time between this mark and this mark is less than 100 milliseconds. So those become assertions that you'll make as a part of your test cases. So whether the tooling takes those constraints rendered in the Marty standard and converts them to automatic assertions, that's a tool-specific question. I don't think I know of any tools that automatically do that. So you would have to, as a part of creation of the test cases, manually render those constraints in whatever assertion action language you have for your implementation of the testing profile.
Okay, so I have a question up here if the slides will be available later, and I believe they are available later. But maybe you could tell us, Bruce, if they get posted on the site along with the videos.
Yeah, so I will post these slides on my site as a PDF, which means you can't play the video, unfortunately, because a couple of videos in there. And this presentation will be up on my YouTube site in a few days after we get that kind of curated video up. So they will be available. And I believe that Jack Stein makes these slides available from the Nkosi site as well.
Yes, yes, he does. I didn't know exactly where the slides show up. I know where the videos go. So that part we have down.
So
With
Jack,
that,
you can say.
there he goes. Please copy that link if you want them, because once the meeting is over, that link will go away and you won't be able to see it for a while. So with that, I don't see any more questions up here. Thank you again, Dr. Douglas, for coming in here and giving us this series and lots of insights on model-based systems engineering. For some of us, you're taking us into areas that we probably hadn't thought about before in our model-based systems engineering journeys. So I definitely appreciate it, and it's that 2x4 upside of the head that says, hey, look at how else you can use this as we get focused in our own areas and don't look beyond that. So I know that
I'm just going to say that I'm happy to provide this. The next and the last session in the series will be on MBSE and safety analysis. And in that, I'm going to talk about the ROML emerging standard, which is the risk analysis and assessment modeling language standard, and how to do that in SysML. So hopefully that'll be interesting too.
Yep, I would guess that it will be, since the last 7 have been. I would guess that you'll just roll into number 8 in the same way. So with that, I'll tell Jack, I think you can stop the recording now, because I think the main part of the program is over and our questions seem to have died down now, and we can let everyone go.
Thank you, Dave.